When volume of the container is decreased, the equilibrium position moves to the side with the smallest number of moles of gas. For example, for the reaction involving dinitrogen tetroxide and nitrogen dioxide, there is 1 mole of reactant dinitrogen tetroxide on the left-hand side, and there are 2 moles of product nitrogen dioxide on the right-hand side. 1 mole is smaller than 2 moles, so when the volume is halved, the reaction shifts left to the side with 1 mole of species. The equilibrium concentration of N2O4 is 0.643 molar, and the equilibrium concentration of NO2 is 0.0547 molar. We write the Kc expression, then substitute these values into it to get 4.65 times 10 to the power of negative 3. Now, when the volume is halved, the concentrations are doubled. Why? Concentration in the form of molarity equals number of moles N divided by volume V. Molarity when volume is halved equals number of moles N divided by half V. To get rid of half in the denominator, we multiply it by 2. But we can't simply multiply the denominator by 2, as we will change the value of the entire fraction. What we do to the denominator, we must do to the numerator as well. So we multiply the fraction by 2 over 2, which is 1. Multiplying any number by 1 is fine, as we don't change the value of that number. Half V times 2 gives V in the denominator. N times 2 in the numerator gives 2N. Hence, we get 2 times number of moles N divided by V. Therefore, halving the volume really means doubling the concentration. Now, when volume is halved, concentrations change. The new initial concentration of N2O4 is now 2 times 0.643 molar, which is 1.286 molar, and the new initial concentration of NO2 is now 2 times 0.0547 molar, which is 0.1094 molar. We write the Qc expression, then substitute these initial concentrations into it. We get 9.31 times 10 to the power of negative 3. Next, we compare this with the Kc value. 9.31 times 10 to the power of negative 3 is bigger than 4.65 times 10 to the power of negative 3. Qc is therefore bigger than Kc. A larger Qc means that the numerator, which contains product concentration information, is too big, and the denominator, which contains reactant concentration information, is too small. Product NO2 concentration must therefore be reduced, and reactant N2O4 concentration must increase. Hence, reaction should shift left to reach equilibrium. At equilibrium, the Qc value becomes the Kc value of 4.65 times 10 to the power of negative 3. Making such a change in volume affects the pressure of the system. But what is pressure? Pressure is force divided by area. When molecules are forced to move about in a smaller region of space, they will invariably bump into one another more, as well as knock into the reaction wall more often. So for any particular area of the container, more molecules will knock into it. Force per unit area therefore increases. That is, pressure increases. Pressure is directly proportional to molar concentration too. Thus, halving the volume means doubling concentration, which in turn is proportional to doubling pressure. Reducing volume, which causes pressure to increase, stresses the system. The change is an increase in pressure. This change upsets the system, which has gotten used to a more relaxed and less pressurized environment. It responds to the change by trying to do the opposite, that is, to decrease the pressure. How? Since it can't change the volume of the container, its plan is to reduce the number of molecules within the container. If there are fewer molecules present to knock into the container wall, pressure ought to decrease. It comes up with a clever plan to convert the species with a greater stoichiometric coefficient of 2, that is, NO2, into the species with a smaller stoichiometric coefficient of 1, that is, N2O4. it shifts its position of equilibrium to the left. Thus, the concentration of NO2 decreases and the concentration of N2O4 increases. Despite changes in their equilibrium concentrations, the QC reverts to the same Kc value as before. Changes in the volume or pressure of a system only affect gases. Concentration of a gas is related to its volume. When the volume of a container is decreased, pressure is increased. The system opposes the change of increased pressure by doing the opposite, that is, by decreasing pressure. It does this by driving the equilibrium position towards the side with the smallest number of moles. Conversely, increasing the volume of a container causes a decrease in pressure. The molecules now have more room to move about. The number of molecules hitting any parts of the reaction vessel wall is smaller. Force over area is smaller, that is, pressure is lower. The system is upset by this as it has gotten used to being in a highly pressurized environment. This is a little like city folk moving to some sparsely populated countryside where the less pressurized, slower pace of life unsettles them. The system instinctively opposes the change of decreased pressure. The operative word is oppose. What is the opposite of decreased pressure? Increased pressure. Thus, the system drives its equilibrium position to the side with the largest number of moles of gas, hoping to increase pressure. While a change in volume or pressure may affect the equilibrium position, Kc value still remains the same. Now for some examples. For each reaction, predict in what direction the equilibrium position will shift when the volume of the reaction vessel is decreased. A decrease in volume means an increase in pressure. The system will want to undo that. That is, it'll want to decrease pressure. Therefore, determine which direction minimizes the number of moles of gas in the reaction. Count only moles of gas. A. We have 1 mole of gas on the reactant side and 2 moles of gas on the product side, so the equilibrium position will shift to the left. B. 3 moles of gas on the reactant side and 2 moles of gas on the product side, so the equilibrium position will shift to the right. C. 2 moles of gas on each side, so the equilibrium position does not shift.